Hi everyone, and welcome to part 3 of our lectures on panel data econometrics. In this particular video, what we're going to discuss is the fixed effects model. So in the past video, we said that, well, one way for us to eliminate the unobserved heterogeneity is through the first differences transformation, through the first differences model. But in this particular video now, we'll go through a different way to try to eliminate that alpha I term. Okay, and this one is a little bit more popular than the first. So say we have, again, our model in the form below. Assume that we implicitly account for that VT term. Then one way for us to try to eliminate that alpha I term, right, is to use what we call means or demeaning, to be specific. So remember that for OLS to be unbiased and consistent, it must be that the covariance between our eta I term, and recall that that eta I term, right, is equal to alpha I plus UIT. Specifically, it's this term there, right? For that eta I term, okay, for OLS to be consistent and unbiased, right, we need that covariance to be 0, right? But since that eta I term contains that alpha I term, which is the unobserved heterogeneity, that alpha I we know is a problematic term, right? We need to try to take it out. And one way we can do it is by deriving the time averaged equation. So we're gonna do time demeaning. So in other words, okay, let me take out the time component of this regression altogether. So I'm gonna take this out, this t out, and what I'm gonna do is I'm gonna average everything out through time. So say I had 5 pairs, I'm gonna divide it by time by 5, and I'll take the average of the average income across the 5 years, right? So basically, I'm taking out the time component of this panel data, and I'm averaging across, right? So that's what I get. And I'm able to derive a time averaged equation. And notice it is no longer 2 subscripts, it's just 1 subscript, just I in this case, right? And I do it for every term in the equation, right? And note that, well, alpha I, right, the average of alpha I is just going to be equal to alpha I, simply because alpha I doesn't vary through time. It's constant, right? So whatever time period you have, well, it's going to be a constant thing. So alpha I does not vary through time. So in effect, that alpha I term will disappear, right? So we're going to be left with just that initial case, right? And this leads nicely into what we refer to as the fixed effects estimator. To derive what we call the fixed effects estimator, we take the difference between the original model and the time averaged equation, right? So this is our original model wherein we have both the subscripts, right? That's the original model. And what we do is we subtract the time averaged equation we derived in the last slide. So we subtract the two, right? And what we now derive is an estimator for the fixed effects model, right? And we can simply rewrite this as this tilde term, wherein this thing here is equal to this thing here is equal to this, and this thing here is equal to this. And note that will cancel out. So we achieved the same thing as the first differences model, wherein we were able to eliminate the alpha I term. In addition, we were also able to transform, okay, it in some way, right? So necessarily, we don't need that much of variation between that to now generate sort of a nicer estimate, which was a problem we were having in the first differences model. We don't necessarily see this here, okay? The caveat for this would be, well, if we remove anything that is time constant, we can't really evaluate the impact of time-specific things on the dependent variable, right? So that's one limitation. Now, of course, one way for us to, one big question to ask is, well, how do we actually do the fixed effects model? Are there other ways that we can operationalize the fixed effects model? The answer is yes, right? we can operate it actually through the use of dummy variables. So that's one way for us to operationalize the fixed effects model. And for example, consider this particular model. Average income is equal to beta naught plus beta 1 green space plus that alpha I term and the UIT. So again, this is our composite error term. That's eta IT, right? If, for example, we have 3 cities, right? Then that alpha I term can be represented by some dummy variables, right? By some dummy variables, meaning that each city has a different intercept, right? It's an intercept shifter if it's a dummy variable. We will only have 2 so as not to fall to the dummy variable trap. Why? We have 3 cities. The base dummy or a base city will take the intercept, and then deviations from that intercept will be the contribution of the other cities, right? By explicitly showing this, we are explicitly saying that there is a different intercept for each city. So instead of having that alpha I term there, let me just provide a dummy variable for each city and call it a day, right? So I don't need to sort of think about the alpha I term. I'm accounting it explicitly in my model in the same way that we accounted for the time dimension initially when we first discussed panel data in video 1. So I'm basically accounting for the alpha I term by putting the dummy variables there. So I'm going to have a different intercept per city. Empirically, right, the least squares dummy variable estimator, just by using dummy variables, is consistent to approaching the true beta, suggesting that OLS is consistent and unbiased if the following assumptions below are satisfied. One is that there is weak exogeneity, that is, it must mean that the regressors and the true error term, the panel error term, are uncorrelated. It must be that the error terms across, across I and J, across many time periods are unrelated. And it must be that the variance of those errors must be homoscedastic. That is, the variance must be constant, okay? In essence, the way we operationalize the regular fixed effects model is just through this dummy variable. Therefore, that beta term will be equal to the fixed effects term. So that least squares dummy variable term will be equal to the fixed effects term. Will be equal to the fixed effects estimator. That is, you're gonna derive the same estimator if you use dummy variables versus if you use the time mean, the time average transformation that we initially proposed as the fixed effects, right? But the advantage of the LSDV in some cases is that you can be able to express it more through the use of the LSDV variance, okay? However, right, if n or t is very large, then we would end up with so many dummy variables. So that's sort of the concern. In the example I pointed out, we just had 3 cities. So estimating 2 additional dummy variables is not that big a deal. But say, for example, you were dealing with a panel data set that involved 100,000 individuals or 200,000 individuals. If you wanted to do the dummy variables approach, well, you would need to estimate, say you had 100,000 people, panel data, you would need to estimate 99,999 dummy variables. Now, that's a lot of dummy variables. That takes a lot of compute power, and that takes a lot of your degrees of freedom, right? So that's going to be a concern, right, as you use those models, right? So that's something to keep in mind, whether you're choosing to use a least squares dummy variable implementation or the time average implementation that we initially discussed. The first variant of the LSDV is LSDV1, which is basically we include all space dummies. So if we had cities, we're going to have a dummy variable for each city less 1, right? So that's the first variant of the least squares dummy variable, right? And in general, it can be formulated using this equation below. Okay. The second variant is you ignore city-specific things. You ignore the unobserved heterogeneity. It's not that you ignore, you can't account for it. But in this case, you just account for time-specific things, right? So that's the time dummies. That was essentially what we had in the initial part 1 video, right? And you can write it like this. So that's the second variant. The third variant, right? Again, second variant, less commonly used simply because we think time component is implicitly accounted for rather. The third variant would be, well, you combine the two. You include both the time component and the space component, right? So this is like the mother load thing. You have both of them all together. But again, if your data, you have a lot of cross-sectional entities and you have a lot of time periods, you're going to estimate a lot of dummy variables in this variant, right? So which is the downside of this whole least squares dummy variable approach. Okay. Now, how do you know whether the use of a fixed effects model is better than, say, just typical using of a pooled regression? Well, there are a couple of things. You can use a Wald's test of linear restrictions, which you formulate as below, right? So you can use an F statistic, which you can take a restricted model. That restricted model is usually pooled OLS. And you can take one of the unrestricted models, which is, say, LSDV1, and then you compute the statistic based on that. And you're able to compare the two depending on which would be better than the other, right? So that's one way for us to be able to test which model should we end up choosing. And essentially, that's basically testing whether the additional risk, the restrictions you let go of, were they important or not, right? So that's what this test is doing. Now, the LSDV and the normal time average fixed effects implementation, those are the two most popular ways to implement a fixed effects model. But they do differ operationally in some regards. In many ways, they will yield the same coefficients, right? Especially when you're dealing with LSDV1. Okay, but they are obviously different in equation form. So if you compare the time they need versus adding time dummy variables, they're different. They look different. And these differences tell us what the pros and cons are of each model specification. Okay, so if we look at the R squared of the time mean fixed effects, the time average fixed effects, and the least squares dummy variables, right? If we have an R squared, okay, equal to 0.8, if we run the time average fixed effects, how do we interpret this? The answer is the R squared is the variation in the average income across time explained by the model. Ergo, how well our model explains deviations in average income away from its time mean. I don't know about you, but that's not generally the most straightforward explanation, right? I'd like to be able to interpret R squared as a pure goodness of fit measure and something that I'm used to, right? If you do LSDV1, right, on the average, we usually will get a higher R squared, simply because LSDV1 will include more variables on the right-hand side, right? You're using more regressors, right? And in generally, the R squared is monotonically increasing with the number of regressors that you have, right? So because you're using additional dummy variables, and in the time averaged one, you're using no dummy variables, well, of course, the R squared will be somewhat higher in the LSDV case, right? But it isn't really a good indicator when we have a lot of variables, again, simply because that R squared being high is just a function of the fact that you're using a lot more variables than in the time average case. Okay. Now, one way for us to show the superiority of fixed effects over a normal pooled OLS is to show it in a graph. And I think this one will bring all of the things together. So consider this model. We want to regress average income against years of experience. Let's forget green space for a moment. Let's use years of experience. Okay. It is obvious that the average income of a person is expected to be higher the more years of experience they have, right? However, if we just ran a simple pooled OLS, i.e., lump the data together and estimate it as if we were one big cross-section, you might come up with a nonsensical result, right? And that leads into the misleading inference of the pooled OLS. So if you notice here, okay, the points there I have, okay, are the data points that I have. So in here I have 1, 2, 3, 4. I have 4 cities here, right? I have 4 cities, and I have 2 years. I have 2 years between the 4 cities, right? And notice that if I just plotted the scatter plot of all of these, right? it would yield me a line that was downward sloping. So in reality, that would tell me that the line is negatively sloped, meaning the higher the years of experience, the lower the average income, which is a nonsensical result. Again, simply because I'm lumping the whole data together, right? I'm not even considering the fact that maybe cities in my sample, right? Some of those cities may belong to developed countries, some may belong to developing countries, right? So I need to take that into account, right? And if we dig deeper, one of the reasons why a regular pooled OLS might fail is because it failed to account for the space and the time dimension which is present in panel data. So what I'm going to do is I'm going to take the same scatter plot, but this time I'm going to label it, right? I'm going to label the data points there. And you can see that the negative line was probably caused by the fact that New York has such a high standard of living that even if we were accounting for things throughout time, New York's standard of living is still higher because it started off way ahead of, say, a city like Manila, which is in a developing country, right? Beijing also, the development of Beijing was fast, right? But it's still far below where New York was, right, back in 2015, right? So what you can see now is, well, we see the general trend is actually upward, but if we have all of these points as just nameless points, okay, we're gonna end up deriving a downward sloping line, which will imply a beta that is negative. But the true probably beta that we should be observing, okay, is an upward sloping one. And how can we get that upward sloping result? It's simply because the fixed effects or the first differences model, which we discussed before, thinks about observations across cities as different, right? Not all these cities are super directly comparable. Because we were able to remove that unobserved heterogeneity component in both of these approaches, we can disregard that there are differences in the average level of income across city, like comparing Manila standard of living versus New York. So that sort of mixture of like nameless things, nameless scatter plot, would not be a problem when we're dealing with an FE or an FT. So when you compare many different data points at varying levels, you may come to misleading conclusions when you look at it as a whole. But when you look at it in parts and account for this unobserved heterogeneity, you'll be able to see it more clearly. So the differences in the average level of income are due to city-specific differences, which really don't change throughout time, right? So what does the first differences model try to do graphically? Well, the first differences model will try to fit a line between these pairs of observations. And notice it will give us a beta that is positive. That is the approach the first differences model is doing. It's trying to account for the fact that those city differences matter, right? And it's going to give you the upward sloping betas that you expect, right? So these are the upward sloping betas that you expect. The fixed effect models will do something similar in that it tries to find the midpoint of all the observations for a particular cross-section I because of this time average property, right? And it tries to connect these points as neatly as possible. Okay. The fun thing is that if we only have 2 years, say, for example, in our example, the fixed effects and the first differences will be exactly the same, right? So it will be that midpoint, so it will correspond to that same line, actually. So that's what the first differences is doing and what the fixed effects is doing. I think it's clear to say that these panel data models think very differently than an OLS that will just try to lump everything into one big blob. Okay. Now, in the next video, we're going to try to explore our last panel data model, which is the random effects model, which is a very specific model wherein it deals with cases wherein we actually can prove that those time specific those unobserved heterogeneity components, that alpha I, is actually exogenous to the regressors, right? And we're going to deal with that in the next video. So thank you for your attention, and I'll see you in the next video. Thank you very much.